Okay, so I messed this up last time and it's not recording the entire thing, but let's try that again. So this is my lab report for the first lab of Physics 2212, which is Physics 2 Modern. My name is Cooper Allen, and this is for Lab Section X21. Lab 1 is the Charged Tapes Lab. The purpose of this lab was to produce a computational model of the electrical forces that two charged tapes exerted on each other, accounting for gravity and, via comparison with real-world data, to estimate the amount of charge necessary on each tape to create an electrical repulsion force that was strong enough to overcome gravity. Or, in simpler words, give two pieces of tape charges, bring them close together, see how much of a charge you need for one of them to make the other one float. Okay. And we are making a few assumptions in doing this. First and foremost, we're ignoring air resistance. We are also treating each piece of tape as a point charge in the center of each piece of tape, as opposed to a bunch of distributed linear charges, a bunch of individual charges distributed linearly along the piece of tape. And we are also assuming each tape to have the same charge as the other one, and for that charge to be evenly distributed along it, because that's what allows us to treat it as a point charge. Yeah. So some fundamental principles here. Newton's second law, F equals ma. You can actually see there force of gravity, Fg, is m times the acceleration due to gravity, 9.81 meters per second squared. And that's what allows us to tell how much of a force we need to be... Okay, I'm not doing that. It does that on its own. I don't know why. How much of a force we need to overcome with the electrical repulsion. So that's the force due to gravity there. Coulomb's law, which relates charge and distance to a force. And then the electric field equations, 1 over 4 pi epsilon naught. Yeah, all that. So those were all important here. Just a preview of our results. We did find that the tapes were positively charged, both of them, and we also found that overcoming gravity required a charge of about 6.603 times 10 to the negative 7 coulombs. Yeah. So here is some of the math that I used. You get a free body diagram over there, and you've also got the link to my code, which you can actually see here. So there is the model that it produced. You can see the force that we needed to overcome. That is actually the force of gravity there, which is the same amount of force as the electrical force. And then the charge on the tape that we discussed earlier. Here's a bunch of code that just outputs what you're seeing on the left. Scale factor of 3 just to make it visible. Yeah. There's... D is 0.02 meters, so that's 2 centimeters. That's the distance at which we experimentally found in the real world that the two pieces of at that distance the two pieces of tape started to interact electrically. But yeah, that's that bit. So that we had these extra questions. What if electrons were positive and protons were negative? What would change in our situation here? And the answer is just absolutely nothing. Because what matters here is not whether it's positive or negative. It matters that the two pieces of tape are the same sign. And it is, as a side note, I believe it is pretty much arbitrary, the fact that we have decided that electrons are negative and protons are positive. But especially if we're doing a 1-to-1 flip, nothing changes here. Because two negatives are going to repel just the same as two positives are. And so our nomenclature doesn't affect the real world. However, it is important to handle the charged tapes as well as possible for a very real reason, which is that you and most of the things that you are going to come in contact with besides the tape are neutral objects, and prolonged contact between the tape and a neutral object is going to neutralize the charge on the tape, which means you're not going to have enough of a charge to create the forces that will be strong enough to overcome gravity, and so the things just aren't going to float, and the lap won't work. And so, it did take us a couple of tries to get that to work, but we did it, and yeah. So just a general analysis of this. The computational model we created, which you can see here, did track very closely with reality, even despite the fact that we're ignoring air resistance and we're treating it as point charges instead of distributed charges. And they probably honestly were not equal charges. There's a very good likelihood that the charge of the first piece of tape that we ripped off the table and the second one were not the same, and that when we put it on the books, something was lost in the middle, but it worked out. And so what matters honestly is just that the computational model did display what we expected and what we hoped. Yeah, so it worked, and that's that. Thank you for joining me in this presentation, and yeah.